everyone. Thank you for coming. Can everybody hear me? Yes, I guess.
Yeah, I can hear you.
So today we're going to hear from Jesse. He's going to present on his project mixing by pattern and age with recurrent mobility for COVID-19. So Jesse is a PhD student at the University of Toronto, working with Dr. Shamista Mishra. He completed his BEng and MSc at the University of Guelph in biomedical engineering, focusing on medical imaging processing, including automated segmentation of brain, MRI, and analysis of digital histopathology. Just as a PhD student, working, Jesse's PhD work uses deterministic compartmental model of HIV transmission applied to sub-Saharan Africa. So his thesis explores how different it is in model structure, especially those related to sex work and different levels of risk, and how they can influence projections of epidemic trajectories and intervention effectiveness. And he has also helped in leading and supporting various modeling projects with Dr. Mishra's research group in mathematical modeling and program science, including studies on turnover of people in sexual risk group, sexual mixing patterns among by MSM I mean men who have sex with men, and using this in estimating the reproduction number of COVID-19 and age neighborhood contact pattern within Ontario. It is really great to have Jesse here today. Jesse, you're welcome to present your work.
Thanks. Thanks, Jimmy, and thanks for the opportunity to present today. I will share my screen again. So hopefully you can all see it. So last time I tried to give this talk, it ended up taking 2 hours. We split it up over a couple sessions, but I'm going to skip one of the kind of aspects about the methodology and just focus on kind of the latter half. But if there is interest to kind of review some of that stuff after the fact, I can go back and we can explore it a little bit. Yeah. So the motivation for this work was that we were interested in quantifying the impacts of vaccine prioritization to specific geographic hotspots within Ontario, and in particular quantifying that with respect or as compared to vaccination rollout strategy that was not prioritized to any geographic patches. So as probably some of you know, the vaccines were prioritized to various neighborhoods throughout Ontario, those with the highest incidence essentially. And this work is basically aiming to quantify the relative impact of that strategy relative to not doing it, or other strategies like age-based prioritization. So to answer that research question, we constructed a transmission model. And when I say we, I haven't had much to do with it. It's been mostly Mackenzie and Sharmista and Hui-Ting. But I've just been supporting this kind of mixing stuff. And that model is basically stratified or takes the Ontario population and stratifies it according to a lot of different dimensions. One of them is this geographic patch, and they're actually defined by cumulative cases of COVID-19 deciles, so ranking them all 153. They're basically like neighborhoods. They're, I forget, roughly maybe 10,000 people in each of these. And it's basically the first 3 postal code digits. So I'll show a graph or a map of those in just a moment. And then those neighborhoods have been kind of grouped into super patches, which actually may not be connected in a physical sense, but for the purpose of the modeling, that heterogeneity and risk according to those different incidence deciles is the kind of key stratification that we're interested in. So that's the way that we've kind of stratified the population with respect to geography. The population is also stratified by age, and those age groups are kind of irregular. They're not necessarily like 10-year groups. And that's according to the vaccine rollout eligibility over the various months throughout the pandemic. So that's kind of the other stratification. And then with respect to the contact types, the model that we're now using only has 2 of these, but the source data that we're using stratifies by household contacts, school contacts, work contacts, and other. And so for the purposes of this presentation, I kind of keep them all separate because it's kind of nice to see how they each look a little bit differently. And then, of course, it has a bunch of COVID infection stuff that I won't talk about today. So what we're interested in doing to support this modeling work in this kind of side piece is examining how many contacts people form given that they are in a particular age group and a particular patch. And we want to know what types of contacts they're forming with these other various age groups and patches across the various types. So as I mentioned, this is the map of the different geographic patches throughout Ontario. And for example, all the blue ones would basically be formed one population or patch within the model, and they'd be substratified by age as well. And then in terms of the COVID case counts per day across these various deciles or patches, those have been relatively consistent in terms of the differences between them. So it kind of justifies and helps us support the fact that these patches are distinct in some kind of unknown characteristics that we will kind of, I won't get into today, but the way that we kind of implement differential risk within each of those patches is kind of another layer to this. But given that we assume that they are kind of distinct populations, we are interested in how many contacts they're going to be forming with each other. So that's kind of the goal of today's work. So as I said, develop a mixing matrix of the number of contacts formed and with whom, stratified by these various factors. So which patch am I in or decile, which age group am I in, and then of course, which other decile, which other age group, and then also stratified by the contact type and the calendar month, because some of these things are changing by time, especially in regard to mobility restrictions throughout the pandemic. So this big matrix ends up being, 40,000 elements times time. So of course we need to kind of make some model to estimate this thing for us. To estimate this huge contact mixing matrix, so not based on polymod age groups. I'm getting to that in just a moment, David. Oh, wait. I see Mackenzie is helping answer my questions. Thank you. Okay. Yeah, so to estimate this big mixing matrix, we start with mobility data, and that's the part that I'm going to kind of skip over today because it has mainly to do with the data itself, and it's not as interesting from a methods perspective. Then we use these age mixing matrices that, as Martin has mentioned in the chat here, we do draw on from the Polymod study. And then we also kind of developed a new way to integrate these two sources of data to actually define this overall mixing matrix. And that's kind of the key contribution, I would say. So I said I would skip over this, but probably the interesting elements are something like this. So each of these different tiles are different months throughout the pandemic. And what each individual tile is showing here is the probability that someone from this x-axis is going to go and visit some other patch on the y-axis here, given that they're leaving their home neighborhood, their home FSA. So you can see that even if I'm in the highest incidence decile, decile 1, if I'm leaving my home neighborhood, I'm probably going to travel to another patch or another FSA. Sorry, I'm using some terminology interchangeably here. I'm probably going to go to another neighborhood or FSA that is also in the same decile as me. And even if I'm not, the next highest probability of where I'm going to go, I'm sorry, it's here, would be another patch that's in, say, the second incidence decile. And the chance of me going to the lowest incidence decile is really small. And this kind of makes sense from a physical perspective, just because there tends to be a lot of homogeneity and proximity of the patches with each other. So the highest incidents are all near the urban areas, and the lowest incidents are very urban, very rural. And you can also see that this kind of conditional probability of traveling here, given that I'm leaving my home, is pretty consistent across time. There are some subtle differences, but for the purposes of kind of projecting beyond the available data that we have, we chose to eventually kind of simplify this as an average basically across these various months. And that's kind of, there were some details in that I'm going to skip over for now. But one of the things that we didn't talk about just now was the fact that that probability of traveling to these various other neighborhoods only considers the probability after the conditional probability that after I've left my home neighborhood. So we also had to come up with a different metric to estimate what proportion of my mobility is actually within my home neighborhood. And we basically estimated that based on a proportion of time away from home relative to some reference period, which you can see here. And so after we integrated that, and it turns out to be roughly 70% of the time spent outside of my household is still within my home neighborhood. And so that's why these diagonals here end up being so dominant, because the vast majority of the time, if I'm leaving my home, I'm still within my home neighborhood. And then even if I'm traveling to another neighborhood, it's still within this same decile or incidence kind of stratification. But there is some spillover effect. And for the purposes of our research question, when we're interested about, if we prioritize vaccine to the highest incidence decile, there still may be some spillover effects in terms of limiting transmission in other deciles because we've kind of prevented transmission earlier in the network. So that's why the amount of mixing between these various patches is kind of important for answering our research question. Please, at any point, let me know if you have any questions or I can clarify anything, because I'm trying to keep it informal, I guess. Just to kind of illustrate, those patterns are still hidden within the background. Basically, on log scale, you can see them a little bit better. So to kind of summarize, the mobility is still mainly within my home decile, as I just mentioned. The most of the time away from home is still within my home neighborhood. And then basically, if you are in the lowest incidence deciles, the urban ones, or the rural ones, excuse me, you tend to have the lowest reduction in mobility throughout the course of the pandemic. So you're still fairly mobile, which kind of makes sense. But you also end up spending most of the time outside of your home FSA. So we kind of hypothesized that these individuals are, or these populations are really traveling long distances for their day-to-day activities. Maybe it's to do with farming, or just because there are fewer amenities close by. So it's more likely you're going to have to travel further. Okay, so that's kind of the crash course, and trying to keep it short on the mobility piece. Next, we want to talk about how we use the Polymod age mixing matrices and integrated them kind of into this bigger, more stratified mixing matrix. So the Polymod study was conducted in 2000, or published, I guess, in 2008. And basically they asked if those of you are not familiar with it, in 8 European countries, they asked people, how many contacts have you had on an average day? And stratified those by your age and that contact's age. And so they kind of constructed matrices that roughly looked like this for these various countries. And also, they had all the demographic data of the respondents. And so what Prem et al. Have done in kind of 2 separate publications is actually projected those contact matrices onto a bunch of other demographic structures, including Canada. And they've incorporated not only kind of population demographic information, but the proportions of the population who are working and the proportions of kids who are in school, for example. And so they've kind of, these contact matrices are quite useful, I think, during the course of the pandemic for simulating the numbers of contacts across these various age groups that people have been using for their various models. So this is the input, and this is kind of projected onto Canada, but one of the challenges that we want is that we're actually interested in projecting that onto Ontario specifically. Another challenge is the fact that these matrices need to balance, essentially. So I don't know if people have heard about this idea of reciprocity. When you assume proportional mixing, it's kind of inherent to the model that the number of contacts formed by age group 1 with age group 2 is going to be equal to the number of contacts simulated among age group 2 with age group 1. But given these kind of empiric matrices, you may be able to tell, just because the matrix itself is not symmetric, this won't actually balance. And so within the model, if you were to use that matrix as is, the number of contacts formed with age group 1 with age group 2 would not equal the other way around. And so in order to kind of correct that imbalance issue, some people call it a reciprocity problem, we first basically unweighted the matrices by the demographic age distribution used by Prem et al. For Canada. And that's basically to kind of undo the inherent weighting of these contact matrices by how many people are in the various age groups. And now we obtain this unweighted CU AAY. And essentially that represents the numbers of contacts that a hypothetical population would form if the population they were mixing with had a square demographic pyramid. So there were as many people at 80 years old as there were at 1 year old. It's kind of just a theoretical thing because later we will kind of undo this effect and properly weight it by the demographic pyramid of Ontario and in fact of the various patches specifically. So that's kind of the first step in this balancing procedure. The second step is enforcing symmetry. So if we have this square demographic pyramid for this unweighted contact matrix, then in order to kind of ensure that it will balance, what we can do is average it with its transpose. And in that case, we get a symmetric matrix, C unweighted and balanced, and that's kind of guaranteed to balance in this case, while still maintaining the absolute or the absolute numbers of contacts that are expected, roughly, again, given the demographic normalization. There are kind of other approaches to enforcing symmetry and that are a little bit more sophisticated. And I kind of actually need to review whether this is the best approach, but for now it's relatively sufficient. And I should say the reason that this is required is basically because the Polymod study originally did not necessarily ensure contact balancing. So if they had any bias in the respondents, how many contacts they reported with this other age group, and then when they asked that other age group how many contacts they reply, that raw data did not necessarily balance. And so that's kind of the source of the imbalance in this in these matrices. And so when we kind of are averaging it, it kind of reflects an assumption that both of those respondents were kind of equally believable and or equally unbiased or equally biased, I guess. And then by averaging it, we're kind of weighting them equally. So that's kind of the gist of it. Oops. Jeez. Classic. Okay, so these were the original matrices, and then after this kind of balancing procedure, it's a little bit hard to see the differences, but you can tell maybe up here in the top left-hand corner of the home contacts, it's now symmetric, and so it's a lot brighter up here. Basically, there are more contacts being formed with older people because, again, this is a square demographic pyramid now, so there are as many 80-year-olds as there are 1-year-olds. The work, you can't tell much different. The school is now kind of more symmetric than it was before, and same with others. So this is kind of the first step of using these contact matrices is ensuring they will balance. And then this is the difference image. We can come back to that later if people are interested. The second challenge is the fact that these age stratifications didn't align with the stratifications that we were intending to use in our model. So it's nice that they're by 5-year groups, but in our model, as I mentioned, the age groups are actually quite irregular. So we have one group that's almost 20 years wide and other groups that are like 5 years wider or smaller. And so how do we actually re-stratify this matrix? Because it's not as simple as interpolating as you would in an image, because the numbers of contacts that you would form with a different age group actually would increase the larger that age group it is. So it gets a bit tricky. Our approach to kind of solving this problem is we took this 5-year stratified contact matrix and we did do bilinear upsampling to obtain a matrix with approximately 1-year age groups, or rather, they're exactly 1-year age groups, but the mixing matrix kind of defined over that region is approximate because we've done this interpolation step. In our model, we were also interested in extending beyond just 80 years old, which the Prem contact matrices only go up to 80 years old. And so we had to kind of like diagonally pad, reflecting an assumption that the mixing patterns roughly have that pattern, especially near the edges. So you'll see it looks reasonably plausible, I guess. And then we do this aggregation from this really high resolution, even though it's a bit kind of artificial, this really high resolution upsampled mixing matrix. Then we aggregate it across the self dimension and the other dimension. And the aggregation operations that we do across those two dimensions are actually different. And that's the crux of it when I said it gets a bit tricky. So if I have a 5-year age group, the behavior, the average behavior for me, the kind of self dimension, you basically want to average across those 5-year age groups to obtain kind of as an average of these 5 years, default behavior. But when I'm aggregating across the other dimension, my potential contacts, I actually want to sum up all those different age groups, because the numbers of contacts that I'm forming with each of them, they're all getting summed together. That's what the contact matrix is representing. So those two operations kind of end up resulting in a wonky matrix for us, because our age groups are irregular. And I'll kind of show that in just a second here. So this is the source contact matrices, home, work, school, and other from the previous slide. And then when we do our upsampling, we get something that honestly seems to me to represent like a very plausible assumption about what this matrix would look like if this was all the information that we had. So I think the bilinear interpolation and, as I mentioned, this extrapolation beyond 80 years seems to maintain very plausible patterns. So I think we're pretty happy with this. And then basically we are going to be averaging across this X dimension and summing across the Y dimension to obtain these matrices, which are the age mixing matrices that we've gone and used within our model. And as I mentioned, some age groups like 12 to 15, they're quite small. And so the numbers of contacts that I would form with that age group would be relatively less. But this age group that's, quick math, 25 years old, or 25 years wide, roughly, everyone is going to roughly have more contacts with that age group. And that's why we have this kind of horizontal streak here. So it's a little bit tricky. And at first, when I got these matrices, I didn't think that they were correct, but they actually are. And then once we get out here in these more regular age intervals, then it seems to be more reflective of what we're used to seeing. So now we have this age matrix re-stratified that we can actually put in our model. And if we look at the numbers of contacts, the total, so basically summing across the vertical, the rows, I guess, of these matrices, then this is how many contacts are expected for each of the age groups. So how many contacts am I forming, given that I'm within this age group? In this case, kind of the biggest change as we iterated through these various steps, we have the original matrices that we inputted as the source. We have an unweighted matrix, so after undoing the kind of demographic weighting, then we balance it, so averaging with the transpose, and then we reweighted, we re-stratified it to be the target stratification in terms of age groups. And then we also reweighted it by the target age population or age distribution. And so you can see the contacts stay roughly the same, but it's also kind of hard to disentangle the effect of a slightly different age demographic pyramid for Ontario versus Canada. So this idea of adapting these matrices to different demographic structures has already been implemented before, and the paper Aragvi et al. Does a nice job of explaining better than I have today for sure, kind of some of the implementation details of that. Our kind of new contributions with this work is the fact that we implemented this kind of resampling strategy where we bilinear interpolate up to this 1-year age groups, including this diagonal padding, and then we aggregated across these two different operations between the self dimension and the other dimension. And then just to kind of clarify that those horizontal streaks are actually expected in this case. So those are the age mixing matrices. Again, these are the two inputs to the final step of our creating this enormous matrix of all these stratified contacts. And so that's kind of the last thing that I want to talk about today. So here on the right-hand side is kind of an illustration of 3 example patches and a way that we have conceptualized of where people might be forming these contacts that will go on to kind of inform how we use these age mixing matrices and this travel data that we have, this mobility data. So for example, we have these 3 patches, and we can kind of conceptualize of this idea of a home pool where I can't form any contacts while I'm at home with any travelers, because basically I assume essentially these reflect the home contacts where I'm not going to have any contacts with travelers to my patch, but I'm just going to form my household contacts, for example. And then this other pool we call the travel pool, where I could be out and about in my home neighborhood and I could meet other people who are also there. Maybe they came from my neighborhood, maybe they came from a different patch and they have traveled there given that mobility data. So it's kind of like a little microcosm here where there's a whole bunch of contacts that could be formed, and the mixing according to age in this pool, we assume we draw on those polymod restratified data. And similarly, we can assume age distribution of mixing within these home pools, but we don't allow travelers to be mixing in the home pools, whereas we do in the travel pools, of course. For our actual modeling work, we assume that only household contacts kind of are formed within this home pool, but you can also imagine that probably the majority of school contacts also happen to be within my home FSA or my home patch. And so there would be justification to explore what proportion of contacts are due to travelers from other neighborhoods with respect to school contacts. And so there would be justification for maybe putting, half of the contacts associated with school within these home pools, where we basically are limiting the amount of inter-pool or inter-neighborhood mixing due to school contacts specifically. And instead, we would associate majority of those contacts with like people traveling for work, for example. And so maybe really the only connections between these different neighborhoods is due to work. But that parameter that we kind of use to say what proportion of these contacts of a given type, and that type index is Y, are formed at home, we denote that with HY. And so for the home contacts, if HY is 1, then 100% of contacts are only formed within this home pool, whereas 1 minus HY or whatever remainder contacts could be formed within this travel pool. Yeah, so that's kind of as I described. And then who is actually present within this travel pool includes not only people traveling from other FSAs to my home, to my pool, but also potentially other people from my pool who have traveled to this. And it's also possible that I have traveled to a different neighborhood where I encountered other people from that neighborhood, or other people from my neighborhood, or other people from a third neighborhood. So that's kind of all the mixing that's possible in these travel pools. So if I'm kind of mobile within my home travel pool, the travel pool within my neighborhood, the proportion of people who are doing that is basically going to be 1 minus HY. So everyone who's not forming that particular type of contact at home. And then it's the mobility matrix B is the notation that I haven't really introduced, sorry. The mobility matrix B when my patch is equal to the patch that I've traveled to. So basically the diagonal of this B matrix. And then if I'm traveling to some of these other mixing pools, the other travel pools rather, then it's basically the non-diagonal elements here, but otherwise an equivalent numbers of people kind of traveling to these various patches. So Here are these kind of like finally some mathy equations, but even then they're pretty simplistic. So who is traveling to some arbitrarily selected travel pool G star? Well, it's the denotation is the population who've traveled to G star who were from G originally and age group A originally, and they're trying to form some contact Y while they're there. So it's this proportion who are having these contacts outside of their home mixing pool times the mobility matrix, so what proportion of them from G have traveled to G star, and then we multiply that by how many people within patch G were also in age group A. So this is like a population size times where they're going and whether or not they're forming these contacts abroad, basically. So that's how many people are in this pool. Then the next step is we need to say, well, let's assume that everyone mixes randomly. If that's the case, then we actually just do an outer product of all the people who have traveled from age group A and patch G. We do an outer product with all the potential other people who have traveled from age group G or age group A prime and patch G prime. And we just normalize it by the sum of all the potential other people. So that ends up giving us kind of the proportionate number of contacts formed between all these various age groups and patches as if they were forming them at random. And then basically we apply this age mixing propensity for a kind of demographically square pyramid on top of that. And we say, well, this is the probability that you've run into each other. Now, how many contacts are you forming with people in these various age groups? And because the proportionate mixing is already implicitly weighted by the age groups of the others who have traveled there because of this term here, then we also, sorry, I'm not explaining that well. If we have a really large age group, the probability of people running into each other or running into someone from that age group is already very large under this proportionate mixing kind of assumption. So this proportionate mixing is already implicitly weighted by the sizes of the various age groups. But when we normalize the contact mixing matrix, that was also implicitly weighted by the sizes of the various age groups when we did that aggregation. And so both of these terms end up being weighted by the absolute size of that age group being, how wide is it? How many ages are considered in it? And so to kind of undo that effect, the last kind of piece here that we need is this unweighting term W. In the code, it's kind of implemented a bit differently, but essentially this just like undoes that double weighting due to the sizes of the various age groups. And so this is how we obtain how many contacts we expect to form between people in these, between patch G, people from patch G and age group A with patch G prime and age group A prime. But all of this is specific to only in this patch. There were only a sub-proportion of the total population from patch G who traveled to G prime to form these contacts. And so this represents an absolute number of contacts that are formed between these different age patch groups, but only those within this specific patch. And so we actually have to then kind of sum up the contributions of contacts from all the different travel pools to actually arrive at the total number of contacts that we have. And then in the home pool, all of this kind of math is the same, except that this term becomes less interesting because the mobility term is essentially an identity matrix, which we can kind of see there. And the H is also 1 minus. So as I mentioned, summing up the total contacts for this particular type, we have those kind of contributed by the home pool and those contributed by all the different travel pools G star. And that obtains kind of the total number of contacts modeled overall, which is not a per person, it's an absolute number of contacts actually formed within the model. Then the last kind of easy step is that if we actually want to obtain the number of contacts formed per person, we can just divide by the population size for that patch and age group. And then that gives us kind of this C, GA, G prime, A prime, Y that ultimately we were interested in and kind of set out to estimate. And so that is the main kind of contributions of this mixing implementation and how we've integrated both this mobility data and the, what's it called? The age mixing matrices from Polymod. And now I'll go to that question in the chat here. I see Martin says, how did you populate the households Canadian census data? Essentially, yeah, we have census data for the actual population size. And so that is what was used to inform the PGA here. We didn't actually use household sizes yet, although it may be used as an adjustment factor for the age mixing by households. Or I think Mackenzie could potentially clarify more where we're at with that, because I haven't, not up to speed yet. So it's a bit difficult to visualize, obviously, the kind of 5 or 6 dimensional matrix. So in this case, we've kind of aggregated across the various patches and reobtained just the margins with respect to the age groups. And you can see that the margins, just looking at age group with age group, look identical to the age mixing matrices that we input to the model overall, which is kind of what we would expect. And similarly, if we look at the amount of mixing happening between different deciles, then they're strongly dominated by the diagonals again, because most people are mobile within their home neighborhood, and therefore most of their contacts are formed within their home neighborhood. And in fact, with household contacts, we've assumed that people aren't forming any of those contacts with people from other patches. And so we have a perfect identity matrix. However, for work and school and other contacts, we have a little bit more mixing between the various patches. And this is where kind of the spillover effects of prioritized vaccination to maybe deciles 1 and 2 and 3 might also then go on to influence contact or transmission within these other patches. And then if we are kind of summing across all contact types, so no longer stratified by home, work, school, and other, this is the total numbers of contacts per person per day, which at face value, 10 contacts per person per day seems kind of reasonable. These are before adjusting for reductions associated with mobility restrictions, and similarly for between the different patches. So this idea of people traveling to other patches, forming contacts there, who may not be with just other people from that patch, it may be with people from a third patch, C, that kind of was already developed before using this model by Arenas et al. And unfortunately, we developed it a year later, but we did make some improvements on it. So the fact that we've kind of integrated these complex age mixing matrices with this recurrent, these mixing pool idea, all in this kind of unified framework, is kind of the main kind of contribution of our work. And then, yeah, and the fact that these things balance, because in the Arenas model, they hadn't explicitly tested for whether the matrices will balance. And so the next kind of steps with this, we're working to make sure that the absolute numbers of contacts formed per person per day, especially during the pandemic, are actually reflective of some surveys that have been conducted throughout the pandemic in terms of just absolute values. And then the other thing is that currently the numbers of contacts assumed to be formed between or by individuals in each of these neighborhoods is assumed to be the same for all those different neighborhoods. Whereas to actually fit the model, given that we are going to need to obtain higher incidence in these higher incidence patches, we're going to basically scale their contacts or some kind kind of characteristic of transmission, whether that's the probability of transmission, but more realistically, it's going to be contacts associated with those, the individuals in those patches, so that their incidence is higher. And that kind of reflects an assumption that it's not necessarily more contacts that they're forming, but it's that there are other determinants of transmission that are causing incidence to be higher in those groups. And it kind of becomes like a non-identifiable parameter where it doesn't matter for the purposes of modeling whether we've simulated as if it were a contact, but so long as for the kind of course of our modeling, we assume that that factor is kind of structural and not changing. And so we kind of approximate it using this contact rate, which I think is a kind of concept that has been done before in terms of modeling. And so thank you. I guess I am a little under time, but please happen to take any questions at this point.
Thank you so much, Jesse. That was breathtaking. That was a great one, and the matrix is so huge.
Yeah.
Yeah. So I was actually gonna ask a question. I think you mentioned that one of the questions I was asking. I wanted to ask about the HY relative to the household sizes, like on average. But you sort of mentioned that you didn't include any household size, right?
So the information on household size is mainly driven by, at least in its current iteration, is mainly driven by these contact matrices at home obtained from the PREM study, which comes from Polymod. So in this case, all households are assumed to be kind of equivalent. And when we are actually using these mixing matrices for answering our research question, that's when we're drawing on household size stratified by which decile or which patch they're coming from, which those household sizes are actually different between the different patches. And we're basically using that as a scaling factor on these patterns, and potentially some adjustment for the actual distributions of who those, like which age groups those contacts are being formed with. Does that answer the question?
Yeah, good. Then I think, so these will probably make the whole matrix more complicated. I was gonna ask about the work, because based on the socioeconomic status, we have different contacts mixing at work, right? So like based on the kind of job and the age. So I was just gonna ask if that was factored in the work metrics.
I'm trying to see if Mackenzie is here. Oh no, she's not. She has been kind of working to integrate some data about the different types of work in the different patches.
Okay.
I would say the closest we've come so far to integrating more interesting data around a work by different patches is that we're exploring what proportions of each patch, of people in each patch, are associated with essential work. And when we see that mobility restrictions kind of reduce the amount of mobility, usually we assume that that is associated with an equivalent reduction in the numbers of contacts. But for essential workers, they wouldn't. And so that's kind of the approach we've taken so far to integrating like census type data on work patterns.
So basically it's like a crude estimate, right?
Yeah.
Okay.
Yeah,
so
we haven't explored different types of work patterns with respect to age, because that could get quite tricky. Yeah.
Good. Then my last question, I don't think I quite got your explanation of HY and 1 minus HY on slide study. Sorry. Yeah. So I was a bit confused. So were you saying that home pool is different from travel pool? Like If you're not in the home pool, then you are in the travel pool.
Yeah, it's the pools. The pools reflect where you might form contacts. So the HY reflects what proportion of the population is expected to form their contacts within the home pool versus within the travel pool. And that proportion is potentially contact type specific. So it really only makes sense to have 100% of household contacts formed within the home pool, of course. And as I kind of probably said, but wasn't as clear about, 100% of the work, school, and other contacts in the model currently are being formed in the travel pool. So in our current implementation, HY is basically either 0 or 1, kind of like selecting these two pools. But in thinking about it, I realized that it really could be more of a continuum where, for example, maybe 50% of schools only have people attending that school who are from that neighborhood. And it's not like kids from other neighborhoods, like neighborhoods being FSAs, have traveled to this, although there may be some. So that 50%, it's a parameter that we can kind of tune, perhaps. Yeah. Did that answer?
Yeah, sure. Thank you. So do we have more questions from the audience? Okay, Martin, your question?
Yeah, I was just wondering, in terms of the Canadian census data, so that's just telling you how big the households in a district are. Like the average, like a histogram basically of how the sort of big the households are, and then you kind of use the Polymod data to kind of try to fill those households with people of the right age groups.
Right. Yeah. Okay, sorry.
Yeah, that's pretty much clarified. I was just wanting to double check that. I was wondering if there was. I'm not sure if it's there in the Canadian census because I've only looked at the UK one. Was there any information on age structure within households you could kind of try to incorporate into the model, or would that be too difficult, or is it just not there?
I think there are some information on the age distribution, or at the very least, I know there is a indication of a multi-generational household being at least kind of 3 generations. And that is information that we would really like to incorporate. However, it is going to be challenging because we don't have an empiric estimate handy, although I actually need to look into it, but we basically would need to, weight these proportions of the matrix even higher, being the contacts between, the lowest age group and the highest kind of diagonals here. We would basically want to increase those contacts if we saw a greater proportion of multi-generational households. And that could definitely be important for the transmission dynamics and the mortality, because if you have a really young population and they have a lot of contacts with older family members at home, then that could be quite important. So, but the main problem is that how do we kind of manipulate this matrix in like a parametric or non-parametric way to kind of reflect that? So I don't think we're there yet. I hope, did that answer?
Yeah. It's just because there's a few issues of lingering outbreaks, like when you had a decline in cases in a few places in Britain, and there was a huge suspicion it was down to multi-generational households in certain ethnic minority groups, and possibly because it was hard to disentangle from the fact that they would have jobs on the lower source, which were more risky as well in terms of COVID. So it was this kind of perfect storm of these two overlapping things and people not being able to disentangle the two. I was just curious from that point of view.
Yeah. It would be nice to have these data stratified, these contact matrices stratified by multi-generational household or not. I think that would be very, although I guess we could like do some kind of hack, like I kind of was alluding with zeroing this out or not, or something like that. Yeah.
Thank you. Just say that we have Felix. Okay. Oh, Felix, we can't hear you.
Yeah, that's good now, right?
Good, good, good.
Yeah,
Okay.
sorry, I've just got some setting issues. So I kind of have two questions. So first one is just, I'm not very familiar with the mobility data. So what kind of, how do you estimate mobility between patches? Do you have like GPS tracks and you can, okay, it's this kind of stuff?
Yeah, I totally skipped over the data source. Maybe you shouldn't have. So basically, we have 2% of Ontario mobile devices, roughly,
Okay.
over that period, January, or basically all of 2020. And we have GPS data, but we suspect it's biased, and the way that a GPS log gets generated is associated with people using the device. So if you open up Google Maps, now you have a ping, but the time when you open up Google Maps, you're probably going to be more mobile. So we kind of did a big investigation into how representative the data were and some ways that we could use the data that would make less assumptions about that. But then we basically aggregated those GPS pings eventually into kind of region defined as their home, basically 150 meters square, their FSA, their neighborhood, or then when they visited other FSAs. And basically we assumed they had to spend at least 2 hours there kind of reflecting work or something like that. So yeah.
Okay, thanks. And my second question was at the step when you combine age and mobility matrices. So if I got it right, you just like assume that when someone moves towards another FSA, you just sample its age from the age distribution of the FSA it is in, right? But in that way, don't you like I mean, you assume that there is some correlation in between the two, like people that move from one FSA to another are probably like people working, so between their 30s and then 50s. So like, don't you like overestimate, for instance, at very low age classes, so like babies or children that are much more unlikely to move from one patch to another, right? Because yeah, you see, so two questions. So like, do you have any way to get access to this correlation between like ages and mobility? And second question, like, don't you just overestimate some mobility between like very important classes of individuals, like those very young people that cannot get vaccinated?
Yeah, that's interesting point about the association with vaccination as well. I actually feel reasonably confident that we're still okay here. And the reason is, well, first of all, I should say we have no access to the age of these mobility data because it's all fully anonymized for privacy reasons. So we don't have that information, but I actually think it's okay. And the reason is, even though people may be, let me go back to that math. Even though these people from a various age group may have traveled in the model to a particular patch, G star, when they're there, they still only form as many contacts as are kind of predicted through this contact matrix CAB. And so we model them as having moved, but even when they get there, the age by age contact matrices kind of still predict that they're going to form, let's say they're really, really young, like they're a baby, that basically forms 0 contacts when they get there, or all the work contacts are still going to be formed by the working age population. And so from that perspective, we think it's okay that like we haven't explicitly modeled the mobility by age groups, but we model the contacts that they form after they're being mobile.
Okay, yes, because you completely exclude all household contacts or all the school contacts in this. Okay, yeah, then it corrects a lot for this case. Okay, nice, thank you.
Jesse, so sorry, I have another question. So this is in addition to Felix's question on mobility data. So my question is, you used the mobility data from January to December 2020. So I was just thinking, like, how useful was this data, or wouldn't the data be biased, knowing that this was a time when the stay-at-home policy was implemented, and then human mobilities were restricted. So I was just thinking, like, how useful was the mobility data?
Okay, next time I'm gonna go through my slides as originally planned because I can answer your questions with them.
Okay.
So these are the conditional probability of traveling to different other neighborhoods throughout the pandemic. And we can see they're actually pretty consistent. Like there's not too much difference. I think another representation of it is here. So does the inter-FSA mobility change by month throughout the pandemic? There's some differences, but I would say the overall patterns are reasonably consistent. So if I'm from FSA 1 or decile 1 and I've traveled, the chances that I'm going to travel to another region in decile 1 is roughly 30% kind of throughout the pandemic. So the conditional probability of where I'm going, given that I'm going to travel somewhere, seems to be kind of pretty consistent throughout the pandemic, despite those restrictions. There are some biases, but this is kind of another representation of that data. So that's the conditional probability. And then other things that we looked at were if I'm going to be away from home at all, are certain regions going to be away from home more or less than other regions, given the mobility restriction? So basically, does the restriction affect certain patches more than others? And yes, they do. But that kind of relative impact is kind of consistent across the different months. So, oops. Yeah, it's not ideal, but we've had to kind of try to simplify this stuff as much as possible so that if we want to project forward beyond the available data, then we kind of implement these relative rates of reduction per decile, given an overall rate of reduction for the population, which we can kind of sample more easily. Yeah.
Thank you so much for that response. Do we have more questions from anyone? Yeah, I think we have a minute or 2 minutes for more questions. Anyone question?
Thanks, guys. And I should say that all the stuff is on, the code is on GitHub, and the paper is in preprint. So hopefully we'll hear back soon.
Okay. Yeah. So, okay. So since we don't have more questions, I would like to say thank you so much to Jesse. That was, is it Jesse or Jesse?
Jesse, yeah.
Jesse, okay. Thank you so much for that presentation.